Hello and welcome. This is going to be our lecture video for the Unit 4 Newton's third law test review. The equations you see at the top here are going to be the same equations provided to you on the test, so we just need to know how to use them. I included all of your kinematics. You don't really need them for this review, but as I've done on previous tests, I might have you redo certain parts of the lab. We did one lab, Newton's third law lab, and that did require a few kinematics. So the formulas will be there if you're going to need them, but you got to know how to use them. All right. I'll trust you to do number one, restate Newton's third law. Let's move on to number two. Identify the action-reaction force pairs in the following diagram. So let's start with a bouncing basketball. So let's go to the moment of that collision because that's where it's a little bit more interesting. At that moment, the basketball is going to push down on the earth, and then the earth is going to push back with an equal and opposite force. And it's that push back that causes the basketball to bounce. And it is equal and opposite to how hard the ball hits. So obviously a ball that's thrown really hard at the ground is going to bounce a lot higher. All right, now we've got our person that's pushing against a wall. So they push against the wall, and therefore the wall pushes back. So there's our action. The reaction is that the wall pushes back. So human pushes against wall, wall pushes against human. But I think we could pick out another one in this diagram, and that's the normal force on this person's feet. So their feet are pushing down into the earth, and the earth is pushing back. Action, reaction. Another one we could draw for every single object is the action-reaction force of gravity. The earth pulls us down, but we also pull the earth back up. All right, now what about a balloon? So the balloon is elastic, and therefore it's squeezing in on the air that's inside. So our action force would actually point in. It's that elastic force from the balloon that's squeezing in on the air, and then the reaction force is that the air is going to push back out. So the balloon squeezes on the air, and then the air pushes back on the balloon with equal and opposite force. And that's why we see that our balloon isn't shrinking or expanding. Although, even if it was shrinking or expanding, it would still be equal or opposite force. It would just be that this reaction force pushing back out isn't being balanced by intermolecular forces that are holding the actual latex of the balloon together. So I made that way more complicated than it needed to be. But the reaction forces are right on the surface of the balloon. All right, so imagine you're playing baseball. If you hit a ball such that the ball experiences 2,000 newtons of force during the collision, what amount of force does the bat experience during the collision? 2,000 newtons. Equal and opposite. If you wanted to, we could maybe say negative 2,000 newtons. If we've designated a positive direction, I would accept positive or negative. I think this is kind of a nice, easy question. Just it has to be equal. Opposite if you want to make it opposite as well. On to question 4. Below we see a person getting out of the boat. What is wrong with this diagram? So it says the action is the person getting out of the boat going to the left, and the reaction is that the boat is pushed back to the right. This actually is not a true action-reaction force pair. And it really looks like one. And I found this picture online as a supposed demonstration of Newton's third law, but these arrows are not pointing in the right direction. So the action should actually be pushing to the right, and the action would be right at the person's foot. The person is going to push back the boat with their action, and the reaction is that the boat pushes back on the person. Now, the action force from our person gets carried into the boat, which causes the boat to move to the right. and then the reaction force gets carried into the person, which causes them to move to the left. But they might not have been able to push as hard as they were really expecting because that boat starts moving, and they might not move as far to the left as they hope. And then, if we've got maybe like a dock right here they're trying to jump onto, they might not make it because they have to push much harder than they're expecting to get enough reaction force to make it to the dock. But these arrows they're actually pointing in the wrong direction. I see this mistake in examples of Newton's third law all the time. Action is what we do. Reaction is how the world around us reacts. If we ever have a human in our diagrams. All right. So explain why it is so difficult to hit a falling piece of paper with 200 newtons of force. Well, the paper can't hit back with 200 newtons of force. The paper can't hit back with 200 newtons. Remember, force is equal to mass times acceleration. So if we have a very tiny mass, we would have to accelerate at a very high rate to get the right amount of force. Well, a piece of paper is just too light. I did the calculations on this, and you have to hit it at a speed of something like 400 miles per hour to generate that sort of force over a pretty short distance as well. All right. Define what a system is and how it pertains, or as it pertains to Newton's law, all of his laws. A system, very simple, is an object held together rigidly, meaning that if I push one part of it, the whole thing will go with it. So if it's held together with rope, that doesn't really count as rigidly. It has to be an object that's like screwed together or nailed together. One block connected to another block with a rope in between, that can't really be a system because I can move one side of it without the other side all moving together. So it moves together. All right. When a soccer ball, the soccer ball kicks back with an equal and opposite force. So why does the soccer ball still move? Equal and opposite forces never cancel, and that's because they go into different objects. The force of my foot goes into the soccer ball's reaction force goes back into my foot, and so they're acting on different objects. So let's just say it very simply, the force pair acts on different objects. All right, number 8. Imagine a chain that is in tension, suspending a 5-kilogram weight. Do the internal forces of the chain cause the chain to accelerate? So I think this first answer is an obvious no. If we just have an object suspended by a chain, let's just draw a few links of this chain. Nothing is accelerating because nothing is moving. Explain how this is similar and different to the problem above. So here we have force pairs, equal and opposite forces. At everywhere where two chains connect, we have equal and opposite forces. All right, but why is this different? Is because we have a whole basically rope of these equal and opposite forces that all balance the equal and opposite force next to it. And it ends with this weight at the end, which is just pulling down, balancing its nearest upward force, and then some sort of anchor at the ceiling that's just pulling up, balancing out its nearest downward force. So although we have force pairs that are going into different links of the chain, they're always balanced by the chain next to it. So that's why a chain that's suspended is still experiencing equal and opposite forces and not moving versus a soccer ball that does move. All right, now on to pages 3 and 4. All of these questions deal with Newton's law of universal gravitation, that force is equal to our gravitational constant G times m1 times m2 all over the distance squared. Sometimes you see that distance as the radius squared, especially when we're dealing with orbiting bodies. So G is the gravitational constant, 6.67 times 10 to the negative 11th. M1 was going to be the mass of the Earth in this problem, 5.98 times 10 to the 24th. M2 is our physics student. That is just a 70, no scientific notation needed there. And then the radius is the distance between the centers of masses, which is the same as the distance from the center of the Earth to the surface of the Earth, because the distance to the center of the mass of the physics student is negligible. So we'll just leave it at 6.38 times 10 to the 6th. All right, just plug these numbers in. Let's see if we get the same number. All right, I plugged it all in and I got 685.9 newtons is the unit of force here. All right, let's try that with the values in number 10, which just adjusts the radius by only 100. And let's see what we get. And I plugged in these numbers and I got 683.8 newtons. So very similar numbers, but going up in a plane caused us to experience about 2 newtons less of force. So that's your answer to number 11. And our answer number 12, which do you think is more accurate, using 9.8 for gravity or doing Newton's law of universal gravitation? Well, it's going to be Newton's law of universal gravitation, because we saw a difference between a person on Earth and a person in an airplane. If we always use the 9.8, then those numbers are going to be the same. But by plugging in the different numbers, we saw a slight difference in Newton's law, telling us that it is slightly more sensitive to the exact conditions of your problem. All right, so our last questions here ask you to kind of think conceptually about our formula. Force equals G times m1 times m2 over the distance squared. So number 13 is telling us that the force between two objects is 16 units, but the distance is doubled. So what's the new force going to be? Well, just think about it intuitively. If I pull them further apart, if I've got two masses that have a certain force of attraction to one another, and then I double the distance between them, that's going to weaken the gravitational force. All right, so it should definitely be less than 16, but just by how much? Well, it got doubled, but this number is squared, meaning that just doubling the distance will make 2 squared, or 4 times the difference. And so we knew it was supposed to decrease, so it'll decrease to be 1/4 as much. So it's just going to be 4 units. All right, it's 1/4 of 16 units. And it's not saying that these are specifically newtons, so we can't go back and find any of these numbers exactly. We just know that it's 16 force units. And now that the distance has doubled, it's going to be only 1/4 of the attraction. All right, so suppose the two objects, again, have a force of 16, but the distance is reduced in half. So if doubling it made it 1/4 as strong, then cutting that distance in half should make it 4 times as strong. So 4 times as strong as 16 units. That is 4 times 16, 64 units. So we can see small changes in distance actually have pretty big implications for force. All right, on to number 5. So the two objects are again attracted to each other with 16 units of force, but the mass of both objects is doubled. So we're going from small objects to really big objects. We would expect the force to get greater in between them, but by how much? Well, both are doubled. Those numbers aren't individually squared, but if both are doubled, that's going to make the numerator 4 times as large. So it's going to again get 4 times, which we saw from the problem above, is 64 units of force. And then number 16. So we've got this person, Dawn Wells, has got a business plan to buy and sell gold. Should she buy the gold at high altitudes and sell at low altitudes, or vice versa? So the correct answer here is to buy high and then sell low. The reason for this is at a higher elevation, gravity is going to have a lower impact, and therefore the gold will be lighter, and you'll get more. If you're buying per kilogram, you'll get more gold per kilogram, and therefore more for your money. And then when you bring it back down to a lower altitude, its weight should go up, and you should be able to sell it for more. Now, I will say that this difference is so tiny that you could never actually turn a profit off of this, but it's an interesting idea.